dear friends, welcome to video lecture in engineering mathematics. So today's topic is Fourier transform. So earlier we have seen definition, basic parts in the Fourier transform. Now today we shall see some examples of this and some prerequisites which we require to find Fourier transform of certain signals. Now here some prerequisites here. So for the continuous Fourier transform, now if you observe the first one, the value of integral 0 to infinity sin x upon x dx is very much required. 0 to infinity sin x upon x, it is pi by 2 for a greater than 0, minus pi by 2 for a negative, the standard integral. Similarly, some formulas of the integration of product of exponential and trigonometric, sin and cos, its primitive is this or integration is this. Similarly, you are having the specific limit 0 to infinity for the product of sin and cos, e raised to exponential and sin, e raised to ax sin bx, it is b upon a square plus b square. Then cos, it is a upon a square plus b square. Similarly, some inequalities, mod x less than a is nothing but minus a is less than x is less than a. Then mod x greater than, naturally it is something like this, minus infinity to plus infinity. This is from minus a to plus a, and this one, it is just excluding this, actually this part and this part over there. Then some properties of the definite integral, it is required here, minus a to a fx dx, it is 2 times this thing, integral 0 to a f of x, if f of x is even function, and it is 0 if f of x is odd function. Similarly, we need Euler's formulae on the complex number. It is this, e raised to ix, it is cos x plus I times sin x. Similarly, e raised to minus ix is cos x minus I times sin x. Then this is gamma function, gamma n plus 1 is n gamma n. If this is required here, the value of gamma half, it is root pi and so on. So generalized root of integration by parts, that is also required all the time, because by parts you are doing already. So this rule states something here, no need of applying by parts repeatedly. So to avoid repeated applications of by parts, we apply this rule directly for the functions of this particular type, x square sin x and cos x, trigonometric function. So these integrations are carried out by this in the Fourier transform. We are coming across many integral of this particular type, that's why we need this rule here, generalized rule of integration by parts. Then DYS rule, differentiation under integral sign, we consider certain parameter to evaluate certain improper integrals that actually coming across in the Fourier transform, and we need to find values of those integrals. We use dy, differentiation under the integral sign, this rule over there. F of lambda is parameter to be taken and we are constant here. Then f dash lambda, it is df by d lambda, a to b, d dabba by dabba. This is partial derivative with respect to lambda of this integrand, and then this is to be evaluated again integrating with respect to value, you are getting the value. Now 13 is again this splitting property of the definite integral, and 14 some values there, sin n pi, it is 0, cos n pi, it is minus 1 raised to n, where n is nothing but integer here, or a is less than, n belongs to natural integer. Similarly, you are having cos pi by 2, it is 1, so these values can be obtained there. But these are important formulas to be remembered while finding values of to solve or to work out some examples on Fourier transform. So let us see few examples here on Fourier transform, Fourier sine transform, Fourier cosine transform, which is continuous transform, and this transform is used to analyze or convert the signal from time domain to frequency domain. Time domain is taken as t and frequency domain is taken as lambda. So the first example, find examples on Fourier sine and cosine transform. Fourier sine and cosine transform. So the first example, find Fourier sine transform and Fourier cosine transform of the function defined as fx is equal to x for 0 is less than x is less than 1, then it is 2 minus x for 1 is less than x is less than 2, and this is 0 for x greater than or equal to 2. So this function, this signal, you have to find Fourier sine and cosine transform for this. So I would just solution for this. I would just write down this as f of u in the form of u or t. So I can write down u as 0 is less than u is less than 1. Then this is 2 minus u for 1 is less than or equal to u is 2, and this is 0 for u greater than or equal to 2. Okay. Now Fourier sine transform. Its basic integral is something like this. This is equal to 0 to infinity f of u or f of t sine of lambda u. Or sometimes it is defined as root 2 upon pi also. Sometimes like this, 0 to infinity f of u sine of lambda u by splitting the function and its inverse. It is written in this form also. So I just split the integral as 0 to 1, then 1 to 2, and then 2 to infinity. It is something like this if you observe these intervals here. So I just split accordingly this thing here, f is lambda, this integral as 0 to 1 plus 1 to 2 plus 2 to infinity. It is something like that, 0 to infinity. This is the splitting according to the interval. It is this actually. If you see the diagrammatically, it would be this 0 to 1, 1 to 2. This is 1, this is 2 here. So here is the function defined here, straight line. It's also straight line, and here it becomes 0. So it is something like this. Here the function first part, second part, and then it becomes 0 there. So 0 to 1, the function is defined as 0 to 1, it is u, 0 to 1, it is u sine of f of u to be replaced there. It is u sine of lambda u du plus 1 to 2, it is 2 minus u into sine of lambda u du plus 2 to infinity. It is 0 sine of lambda u du. So this becomes 0 naturally. Now I take this as capital U, this is V, this as U and V, and I apply by parts here. Integration by parts I'm going to apply. Now you know the rule there, U into V, this is equal to U into V1, capital U analytical, U dash into V2 plus U double dash into V3, minus plus alternatively plus and minus signs. And these are derivatives here, dash means, and lowercase suffixes stands for integration. So what I do here, I integrate by parts. This is integration by parts or generalized rule of integration by parts. It is called advanced rule of integration by parts. Now I integrate this. This is u first function constant v1 integration minus cos lambda u upon lambda. It is this minus derivative of first function means u dash, it is 1. Integration again, this is sine of lambda u divided by lambda square. And next would be 0 because derivative of 1 is 0. And I close the bracket here and limits applied 0 to 1. Plus, it is something, next is 2 minus u is constant. Then integration of sine minus cos lambda u upon lambda minus derivative of this function again, it is u dash, so it is minus 1 and integration of this, so 2 minus u minus integration of this minus sine of lambda upon lambda square. And next term would be 0 naturally, so 1 to 2. Now I just apply the limits there, upper limit minus lower limit. Now if you observe here, this is minus minus plus, it becomes here also minus minus plus. Now I apply upper limit 1, u is replaced by 1 there, means 1 minus cos lambda divided by lambda plus sine lambda upon lambda square. Lower limit if you put here, this becomes 0 and sine 0, its value is 0. So need not be considered the lower limit. So this is minus 0 and plus here what happens, see, if you apply the upper limit 2 if you apply 2 minus 2 is 0, then this becomes 0. Then here minus sine 2 lambda upon lambda square and 1. If you apply 1 there, then this would be, see, 2 minus 1 is 1 minus minus plus, because there is one more minus sign of the lower limit. So it is cos lambda upon lambda and this one, this is minus minus plus again. Sine lambda upon lambda square. So this is the way you can just observe these things here. So this gets cancelled from here and you are getting answer. This is 2 times because this one term and this another term here, they are same. So I make it 2 times sine lambda divided by lambda square minus sine 2 lambda divided by lambda square. Or I can write down this as fs lambda is equal to 2 times sine lambda minus sine 2 times lambda divided by lambda square. So this is your required image function, or this is required frequency function for this, actually for this particular signal, or this is required Fourier transform. Okay, now we go for the next example. One more example we shall see. Second problem. Similarly, you can find out cosine transform of the same function as it is mentioned for your cosine transform. It is mentioned earlier for your cosine transform. For your cosine transform fc lambda, it is defined as 0 to infinity this f of u into cos of lambda du. You can find out this. This actually we split by the same way, 0 to 1, 1 to 2, plus 2 to infinity. Then f of u we replace there. It is 0 to 1, it is u cos of lambda u, plus 1 to 2, it is 2 minus u into cos of lambda u du, and plus next is 2 to infinity, it is 0 cos of lambda u into du. So likewise, you can just integrate by parts and get the
transform, cosine transform. As usual, it's very similar to the earlier one, that is sine transform. Okay, now shall see some more examples here. Find Fourier cosine transform, Fourier sine transform of the exponential function f of x is equal to e raised to minus x, or mod x we can take for x greater than 0. Okay, and hence show that 0 to infinity x sin mx divided by 1 plus x square dx. This is equal to pi by 2 e raised to minus m, where m is greater than 0. So you have to find out Fourier transform of this. So here it is taken as e raised to minus mx. So let us see this solution for this. Okay, we take this as x here. F of x given. F of x is equal to e raised to minus x, or f of u is equal to e raised to minus u. Fourier sine transform, its basic definition, 0 to infinity f of u into sine of lambda u. So due to the time, I just reject this for time being. F of x is equal to sine transform sine lambda u. So this is equal to 0 to infinity f of u e to the power minus u there, sine of lambda u d. Okay, so I integrate this. This is using the formula as I said earlier, 0 to infinity or e raised to x sin bx. This formula is e raised to x upon a square plus b square inside the bracket a sin bx minus b cos bx. This formula we are using. So it is a is equal to minus 1, b is equal to lambda. So I write down the integration of this, e raised to minus u divided by 1 plus lambda square inside the bracket minus sine of lambda u minus lambda into cos of lambda u, and limits applied 0 to infinity. So I apply the upper limit minus lower limit here. If you apply upper limit, it would be if you apply upper limit infinity, e raised to minus infinity straight away you are getting, and e raised to minus infinity, you know, it is something like this, 1 upon infinity, and it would be 0. Okay, so upper limit, its value to be 0, because 0 multiplied by the whole expression to be 0, and lower limit, it is minus e raised to 0 is 1. Okay, 1 plus lambda square inside the bracket. If you apply limits here, sin 0 would be 0 minus lambda cos 0. This value is 0. This value for lambda is equal to 0 is 1. So you are getting this 1 bracket complete. So you may be getting this as lambda upon lambda square plus 1. This is fs lambda. So this is required Fourier sine transform of this.